Okay, welcome back to Thevenins Theorem Circuit Video 3. This is quite a daunting challenge to not over-document, but I'm going to actually work through our very first really simple series circuit that you see on the left. And we're going to prove that a Thevenin circuit, which is located on the right here, is going to be the same voltage, the same current that is delivered to the load of a Thevenin circuit. Here we go. You see, they're equal. We're going to run through the computation and take a look at this, see if this is really true. Now, the reason I picked a series circuit to Thevenize, you would never do this. A series circuit is way too simple. It's a series circuit. Chapter 5. Just work it. There's no need to Thevenize it. But from a learning model, the series circuit is far simpler to grasp what's going on before you get into something a little more challenging, like a series parallel circuit. Thevenins was made for series parallel breaking down of circuits. So, as it says in the middle, we're going to prove that a complex circuit can deliver the same current and the same voltage to a load. And our goal is to take this load here by the mark X in red and be able to change that load. You see, down here, we might want to solve the same circuit 3 times, 5 times, 10 times, 20 times. We don't know what people in the real world want to do and why they want to do it, but they might. Why would you want to solve circuit 1 up here when you could drop those 5 load resistors shown below into the circuit called a Thevenin circuit? That would make more sense. Do you remember over here? We had pre-calculated that value and got the... Here is our simple series circuit. You would solve it the old-fashioned way. You really want to get a jump on this? I'm hopeful that you know how to find the current and the voltage of this circuit. I've gone ahead and calculated the total resistance here in blue as 11,000 kiloohms by just simply doing old-fashioned circuit analysis. I have included the resistor in the circuit, the load resistor, and it's in there because we're trying to find the current and voltage through it the old-fashioned way. We used Ohm's law to find the current of 0.909 milliamps, and we used Ohm's law to find the voltage at the load. Didn't have to. We could have taken this circuit and taken that element circled in green and used the voltage divider and taken the 10-volt battery and multiplied it by RL over RT. And that would have given you 10 volts times 1K over essentially 11K. And that would have given you that voltage. So we could have used voltage divider. Once we had the voltage, we could use Ohm's law, like we did over here, to calculate the current. Understood? So, the solution that we're heading towards, like I said, this circuit is not complex. But if you needed to solve something very complex, the solution would be to Thevenize a circuit, and then multiple computations, multiple calculations become easy. Same answer. Okay, so here's our first exploratory of calculating a Thevenin circuit. I want you to be forewarned that weird values come up when you're trying to Thevenize things that are too simple to Thevenize. A series circuit is one of those things. Now, we have a 10-volt power supply up there at the top left, and I have taken the first step in that circuit. If you look at your steps to Thevenizing, number 1, remove the load. I did. It's open circuited right here in the green circle. I've removed it, and I'm going out to find the voltage that appears where the green circle has been drawn, where the red is now going in. I want that voltage. It's a 10-volt battery and nowhere to flow. Most of you probably know that 10 volts will float out there. That is our Thevenin voltage. Strange but true, only because it's a series circuit. If it was anything else, it would not be the same as the original battery. Okay? So now we move into step 2, where we look to open the analysis up to our Thevenin down here. And the first step in Thevenizing a resistance is to open the circuit and short the battery, which you can see I've done in the middle of the page on the left. I've actually shorted the battery, and I have a series circuit with an opening because I've taken the load out, and right where I've circled in yellow, I've put my eyeball, and I'm looking back in reverse fashion, trying to calculate the voltage, the resistance of that circuit. And what I see with my eyeball is just 4 resistors in series. So I scoop them up, 2K, 1K, 4K, and 3K, and I get 10,000 ohms. That is my Thevenin resistance. Again, not hard, but not hard because we're Thevenizing a simple series circuit, and I want you to get the basics down before we move into something a little more tricky, shall I say. Okay? So, what we're going to do now is take the Thevenin circuit that we created, which is checkmarked in green. We created that. We calculated the 10 volts, we calculated the 10K, and now it's time to follow the Thevenin steps, which says, once you've got VThevenin and RThevenin, drop the load back into the circuit, and you've got this huge Chapter 5 circuit, a series circuit with 2 whopping resistors. You calculate the current, bingo. Same value you got a couple of slides ago, we've got with our Thevenin circuit. Does it surprise you? Then we go and we use Ohm's law here to calculate the new current times the 1,000 ohms that we dropped in, and we get the same voltage. Does it surprise you? No, it's supposed to work that way. We get the same voltage and current whether we study the hard circuit or the easy circuit. Wow, that is impressive. So let's summarize. Take a look at the data between the 2 circuits. They're the same. Remember, the complex circuit does not work like the simple circuit. This is only good when analyzing on paper. You cannot build this circuit with the red check mark. You cannot build it and expect it to function the same way. But if I only want to analyze this resistor and find out what current and what voltage would it see in a given condition, that circuit, the simple circuit, is essentially a simulation, delivering the proper current and the proper voltage to the load. Interesting. So, what's the benefit of this? So in summary, the complex circuit is solved only one time to create, typo, a Thevenin circuit. And that takes a little bit of time. That's okay, because then every other load resistor that you drop in is now easy and becomes a simple series circuit with only one resistor or two resistors in it. To re-summarize, imagine solving the series circuit on the left, which is not a big deal, to be honest with you. Remember, we're learning something very simple right now using a series circuit as a learning model. Imagine I want to plug all those resistors into this spot right here on that complicated circuit. Wouldn't it be easier doing the green circuit here and plugging into the two-component circuit? Which would you rather do? Remember, we are just looking at a simple series circuit. What if we had something a little more meaty? Would this convince you? Imagine that you have this load sitting there in the middle, and you need to remove the load, short the power supply, solve that circuit. To find that a resistance using Thevenin would create this simple solution for you, and then you would drop the load in. Or you can just choose to solve this circuit the old-fashioned way, which is very, very hard.